Right, okay, welcome everybody. This is really an introduction, it's very, very short. So what I'll do is I'll just show you MATLAB scripting, really very simple script, just particularly the live scripting bit, and then do a Simulink as a programming language, just interface, and I'll do a simple thermal model of a battery using transfer function blocks. These are the standard blocks. And then I'll do a buck converter using Simscape, specialized power systems block set, which is more like a circuit diagram. Before I go into that, I'll just go into MATLAB. I mean, this is what you normally get, and normally you would, the old version started with myself was you write a script like that, and you can type a script and and basically set z equal to x plus y, and you run it, and it will give you answers. Okay, well, you need to save it. It's fine. It gives you answer down here, which is the old-fashioned way of doing it, or you can go into a live script, which I personally prefer, because this allows you to have it like basically a worksheet. So you go into text, and for example, you insert a title, and you just, and then you add some notes, and then you go, okay, I want to add a bit of code. So you go x equal 1, y equal 2. I'm just going to do some simple examples. Z equal x plus y. And basically you run that, and it will give you the answers here, and you can plot graphs. And the nice thing about this is that you can basically go in and export it as a PDF or a Word or a HTML or LaTeX, and then you can use that as a report. So you can have a report this, and you can hide these bits. So you can just embed the graphs in here and so on. So I personally like this, because unlike the old scripts where you can add notes, if you go to the old scripts, you want to add a note, then you basically have to put a percentage sign and type a note here and so on. So you can do that. You can add notes in the script, but it's not as nice and presentable as the live script. So I thought I'll just introduce you to that. Now, obviously, I'm not going to teach you how to program in MATLAB, but it's very similar to C, essentially. So I don't know if you know C or any programming or Python. It's really quite similar. So I'm not going to do that. I'm going to focus on Simulink, which is essentially the I call it graphical programming language. So if I start a blank model, what you get is something like that, and then there is a library of blocks. And at a basic level, what you can do is you can have what we call sources. So, for example, a constant of 1, and if you right-click and drag this, you get another 1, and then you can add a maths operation, and for example, you can add them together. I'm just reducing the basics here, and then of course you can view the result and say I want to view the result, I display it. So you basically run this, and of course it's going to give you an answer, which is 2. Okay, so it's obviously you can write that in a script very easily, and it's pointless doing such a calculation of adding 2 numbers together. But the powerful thing about Simulink is it can do integration, and I'm going to illustrate that by a couple of examples. So the first example I'm going to do is this one, which is a transient thermal model of a battery. So it's really, really very, very high level. Essentially, this is a battery. I'm modeling it as a box. It's got some losses inside. I'm calling them Pin. So these are just heat generated within, and heat being lost on the outside. These arrows represent that, and I'm just calling that P out. And it's just simply conservation of energy, Cp, the specific heat of the battery, times its mass, dt, rate of change of temperature is equal to Pn minus P out. So it's very basic first law of thermodynamics. And I'm going to assume that the P out, the lost heat, is essentially proportional to the temperature difference between the temperature inside the battery T and the outside temperature T naught, divided by a thermal resistance R. And I picked some numbers which I think are reasonable. Cp is 1130 joules per kilogram Kelvin for a lithium iron phosphate battery I picked up from the internet. A mass of 4 kilograms, thermal resistance of 0.2 kelvins per watt or degrees per watt, and an input or heat loss of about 100 watts. So it's a very basic thermal model, just looking at the transient response of the battery. And this is the equation, and what I've done is I've just substituted the loss with the temperature difference divided by resistance. And if you arrange that equation, divide by Cpm, you get this equation, dt equal 1 over Cpm Pn minus 1 over RT 1 minus T naught. And that equation you can translate into this graphical diagram. So here Pn, that's Pn here. So if I just get a, oops, sorry. Let's go back. Get a pen. So Pn here, and I'm literally implementing this. This is P out, remember, this is P out. So P out here, Pn minus P out is equal dt, but P out is essentially equal to 1 over R, which is 1 over 0.2 here, multiplied by T minus T naught, and T minus T naught is coming from here T, and I'm taking minus T naught, which is 300 Kelvin. Now, that divided by 1 over mCp will give you essentially, in fact, so dt is here. So it's one error there, right? Right, so I'm basically implementing this equation graphically. I'm taking the Pn minus P out is equal to 1 over R T minus T naught, and T minus T naught is basically T here minus T naught, dividing it by 1 over mCp, which is this figure here, and I'm getting this derivative. And if I integrate that, which is 1 over S in the Laplace transforms, gives me temperature. And of course, I can use that to subtract from a T naught and then implement the rest. It's just really rearranging the differential equation to translating it into a graphical model, which is transfer function model. Now, in terms of the mechanics of doing it, if I go to MATLAB now, and I have an empty model here, and to help us with the equation, just to remind you of the figure, I just put it in there at the bottom, right? And I'm going to create that. So essentially, I'm going to start with Pn. So that's what they call a source. So in that case, it's constant. and that has a value, if I double click it, of 100 in our. You can make that into, by the way, a symbol and assign it differently, but I think at this point I'm not bothered with making it too advanced. So I can call that PN, and then there are many shortcuts, so I'm just going to do it the boring way, easy, slow way, I mean. And you can go to a math function and see what subtract that. So this is subtract coming this bit here. Okay, and I want to divide that by 1 over MCP, so that's called the gain function. So multiply it really by 1 over MCP. So I multiply that, and this is 1 divided by 1140 times 4, the number there. And that's that. Now, it doesn't show you what's inside, but you can enlarge it to see what it is. So this is 1 over CPM or MCP, right? And then you integrate it, so that goes to continuous, and then there's an integrator here, and you integrate that, and that gives you, well, obviously this here, I'll label it correctly, is dt, and this will be t. You can view that temperature. It's called sinks, the viewers, and I'm just going to put a scope this time, so I can view what's going on. Now I need to complete the feedback loop, or what looks like a feedback loop. So there is another subtraction. You can copy by a block by right-clicking and dragging, and you can rotate it by putting Control R, and that rotates it. And that basically is subtracting temperature T from T naught. So I need another constant, so I can just copy that block. And it's basically T naught, which I'm going to make 300. And then multiply that by 1 over 0.2. So again, one of these. 1 over R. Oops. And this is basically 1 divided by 0.2. So it's very easy, really. I mean, it takes a bit of practice or for you to do it so quickly, connect things together. I don't know where you are, but once you've constructed that, it's very easy, right? I'm going to run this model for, I think I ran it before, I can't remember how many seconds. So let me switch to the one I made earlier, which is very essentially the same. It's 4,000 seconds. Okay, so I need to put 4,000 seconds there. It's a long time because it's got a long time constant. It's very quick. I'm just going to look at the temperature. And you can see the temperature there, it has risen because I started from 0, it has risen eventually to just over, well, probably about 320, so 20 degrees. And you can play around with this and see what you can, you know, if for example, you can improve the cooling or or make the cooling worse, let's say 0.5, and you should see, just to see if it makes sense, it will be a bit hotter. Well, it's taking longer for a start, so if I make it 10,000, for example, it's now getting 350 because I'm making the cooling worse. And you can play around with that and what changing different things makes. Yeah. Right, so back to the presentation. So this is what I was showing you, the simulation for that. The next example is just a very simple buck converter, open loop, not very complicated. So this is a DC-DC converter. So
sorry, Suleiman, can I ask a question? See if you can go back one slide. Right, see that image there that you've got on the screen, whereas the one in Simulink was a black background. So how did you pull that?
Okay, it's a very good question. It's very easy actually. If I go File, copy to clipboard, sorry, Control-C.
Yep.
When it copies it, it comes automatically in black and in white and black.
All right, okay.
With a white background. Yeah, you don't need to do
cool.
anything. Yeah, it's just basically Control-C.
Okay.
I mean, another thing with figures, I mean, obviously you can jazz them up. So if you go here, you can, you know, put axes, label the title, for example. So still, so I can make this temperature, for example, in Kelvin or something. You can see it's at the top there.
Yeah, okay.
You know, you put time in seconds and you know, all sorts of things.
All right, good stuff. No, thanks for that.
Yeah, that's okay. Yeah, so the buck converter example is a very simple DC-DC converter. So there's a battery here, an IGBT, a diode, and an inductor and a capacitor, LC filter, and then there's a load. I'm assuming it's a resistor. So it's very, very simple setup, and we vary the duty cycle of the converter using this PWM generator. Now there are two libraries in Simulink. There is this the block set, which is basic Simscape, and there is this older one, which is called the Specialized Power Systems block set, which doesn't look as nice and as neat as a circuit diagram. So it's a nice circuit diagram, but it's actually much easier and to use and much more powerful for simulating power electronics. So I'm going to give you a demo of that. So we're going to create this circuit and run it in MATLAB Simulink. So if I go to here and just create a new model. Now that, so I'll just make it a bit bigger. So in here, so you've got the basic Simulink, which I was showing you just now with the transfer function blocks and all of that. And they've got toolboxes, they call them. And there's no way I don't even know all the toolboxes. I know quite a few of them, but the one I'm going to show you today is the Simscape, which actually can do a lot of things: electrical, gas, hydraulic, magnetic, mechanical, thermal, all sorts of simulations, fluids, multi-body, etc. So, you know, it's quite involved. I'm just going to focus on the electrical side of things. And as I said, there is the basic library like that, but I'm going to go to the specialized power systems one, which I think for modeling batteries got very more detailed battery models than the other, and power electronic models, and more block sets in there. So in there, the specialized power system So I'm going to pick a source, and you can see I'm just going to pick a DC source. You drag it there, and then I'm going to go into power electronics and pick a buck converter. So there's a block already, and of course you can make it out of basic diodes, and there's should be an IGBT model. There's an IGBT. We can construct that from individual components, but also it has its own already circuits, if you like, standard blocks. So I'm just picking one of the standard blocks. Why make it harder for yourself? So this is in the wrong direction, so I need to flip it. Flip left to right, so that I can connect it to the battery. Again, connections are easy, so you just connect like that. And because this has an enable function in it, so you'll find that, okay, on this block there are two types of connectors. There's the connector which looks like a little square. That's a normal circuit connection, which I did here. And then there are these connectors which look like arrows. These are Simulink block connections. So you can't connect the circuit to that, and you can't connect a Simulink block to the square connector. So I need to get a constant here, because if I don't connect anything to this BL, which is block, it will basically disable this. So I'm going to make that 0, logic 0. It means I enable this diagram. And then we need to connect, bring an inductor, so back to Simulink. And there are basically passives here. So I'm just going to go to the passives library. Oh, sorry, no, we are on specialized elements in here, right? So there's an RLC branch. It doesn't do a single one. It's always RLC branch, and you basically double click on it and see what it's an inductor. So I make it into an inductor. So I'll leave the value as it is. So an inductor there, and there is another one of these which I need to be a capacitor. That's a capacitor, and okay, I need to move that there. Okay, and then there is a resistor. So keep one of these again. So this is a resistor. I'm keeping the values, the default values. It doesn't really matter. And then we need a diode just to complete the circuit. So it's a diode for power electronics. Just get a normal diode. Oh, sorry, it doesn't need a no, what am I doing? The diode is already there, built in. So here we are. So we just need to connect this to that. Okay. It's a bit fiddly. Here we go. It picks that up. So that's, you need to imagine it's looking, just to remind you, this is how it looks like. So this looks like this. I haven't added the measurement yet, but basically there's a diode, inductor, capacitor, and the IGBT. In here, you can imagine the IGBT is, is vertical, and then the diode. So there's a diode connected at this point. So this is the thing about using these blocks. You need to understand this diagram inside here, right? So I'm just going to go back to that model. What this model lacks is measurement. So what we're going to look at. So we have some measurement. essentially probes, and I'm going to measure voltage. So I'm going to measure the voltage here, and then I'm going to measure the current. So the current needs to be in series, so I'm going to get the current in here. Okay. So I'm measuring voltage and current, voltage at the input and current in the output. And you can connect them to a scope, these ones. See, the output of these is now converted from the squares to this arrow. So you connect these to a normal display, so I can put a scope. So if I go to sinks, I just get a scope. And I need two outputs on this, and I just I need two inputs rather. Sorry. So I have two inputs on here. So I have the voltage and current, and I can drag these directly and connect them like that, voltage and current. But it can get really messy with the lines crossing like that. So what I'm going to show you is labeling. So rather than dragging and connecting, what you can do is go to signal routing, and you go to. So this is just labeling this. I'm going to call that V. And I'm going to have another one and call that I. And then from, so go to and from, so this is from, I'm going to pick that as V, and I'm going to have another one of these and call it I. Okay, so now we don't have to make those connections. It's just sometimes it's much neater to not have all of these things lying around. Now, if you try to run this, and I deliberately didn't do the first step, you get an error, right? Now, there is a fundamental thing you must remember with this block set, is that you need to bring in this block and the power GUI, and that tells the software that these are specialized block sets. If you don't do that, it will give you an error. The other thing with this library is that, again, I can run this as it is. It's going to give you some really strange results. So it's giving you some interesting results. Okay, it's not giving you anything. This is where it gets really tricky with simulations. I'm just gonna, there are a couple of things that you need to adjust. Although it says everything is automatic, it never is. So I'm just gonna go to the right one. Right, the first one is the stop time. And here is 0.1, but also it's the setup of the model setup. Right. So in the model settings, well, first of all, I forgot to add the modulator. So I'll do that in a minute. Okay, let's do that. Let's go back to our model that we're constructing. We need to add the modulator, of course. So the modulator is control and measurement. So PWM pulses here, and I just want a simple DC-DC converter modulator. Again, the blocks are made for you, so you don't really need to do anything. And this is basically setting the duty cycle. I'll set it at 0.5. And if you try to run this as it is, it's going to give you nonsense results. So you need to have a reasonable time scale. I'm just going to make it 100 milliseconds, 0.1. Okay, and of course the modulator, I need to set the frequency. I'll set it 10 kilohertz. For these parameters, it's a reasonable frequency. And this one is 100 volts, we said, yeah. And then the settings here are very important, because that very often, if you leave it on auto, it gives you some nonsense results. So the main thing to set up is the minimum time step, 1e-6, typically for power electronics, and the relative tolerance of 1e-6. If you don't do that, it'll give you some, it doesn't switch correctly, it doesn't, automatic setting doesn't really work. So now if we run that, look at the output. Okay, it's giving us a lot of information. This is the voltage and the current. So what we can do is arrange them to be two graphs, for example. So that's the voltage and the current. And you can zoom in to have a look, for example, at, you can see now it's switching the voltage 50%, and there's a current ripple there. And if you want to see the overall picture, you just go and select that, and it goes back. You can see the transient. Yeah. Okay, well, that's it, folks. I didn't want to make it too complicated. So this is the model, and I basically showed you this. Yeah.
Yeah.
So hopefully that was useful. I mean, obviously, it's a taster.
Mm-hmm.
Not a comprehensive tutorial, but
Can you just comment? I mean, someone from previous, and again, that was very useful, because although I've done some of that stuff, it's been a while, so that's a good reminder. In terms of choosing the solvers, because sometimes they're a bit of a black art in terms of choosing an appropriate solver for things. Do you want to comment on that?
Yeah. I mean, here it does. It's better at auto selection, but it doesn't always work. You want to basically if you're doing power electronics, you want to go stiff, one of the stiff ones, stiff. And what tends to work really well for most things is the ODE23T. But one of those. Well, if you go continuous, you're in deep trouble. It's not going to work.
Right, okay.
Any of these 1.5 or 2.3S, or should work for this case. The other thing very often that happens is you get zero crossing. You need to do zero crossing control. This is when you're switching too fast, and then you need to go adaptive to make it work. In this case, a simple model is not going to trouble you very much. So it has its quirks, but I think the auto solver now is not bad. Now, when we are in continuous now, and it's okay for a small model, but if you have a complicated one, you probably want to go to discrete. And have a, let's say, sampling rate of 1e6. That is much faster simulation. Obviously, it doesn't capture details, but unless you have that, so it has given us more or less the same thing in this case. But you can see the ripple is not really as detailed, right?
Yeah, okay.
So you need to be careful with this. So if I make it 0.1, 0.1, you probably see some more details on that ripple. Yeah, you can see it. No, it hasn't really. Oh, okay. Probably is okay, actually. Probably is okay. I wasn't zooming enough. I thought there were only 2 points on it. Yeah, so basically there are many kind of things you can do, and what I haven't done here is, of course, feedback control, so you can measure, the voltage and current and do a two-loop system and so on. But and there are many things in there that will help you design the control system. But hopefully, there's just a taster, quick. If you need some more detailed advice, happy to answer your question.
No, that's good. Thank you, Suleiman.
Yeah, it's okay. Right. Any other questions or comments? Or
but with Simulink, one of my understanding is you can link things you've made together. For example, a model in MATLAB. How would you import that into the where would you choose that from?
So if you go to the library, which is and one of the blocks here, standard blocks, I have to find it. Basically, a MATLAB function.
Okay.
I user defined functions, right? So you get a MATLAB function, MATLAB S function, and essentially a program in MATLAB, right? Interpreted MATLAB function, yeah. And you define in the function the inputs and outputs, and we link it to here, right?
Okay.
And similarly, you can write within MATLAB script a call to run a Simulink program and get some variables back.
Okay.
Yeah. So yeah, I can't remember the commands. I can try it now, but I need to. I think it's not something that I do regularly. But yeah, you can do it either way. So either you call a Simulink model, and basically it will have inputs and outputs, and there's a particular code for it. Or you within MATLAB, so I can, for example, have one of these, and I can just say, okay, calculate the power. Okay, well, so I mean, a simple one, signals and routing. Now, this has one input, but what you can do is you multiplex them to turn them into a vector.
Okay.
So you have V and I, right? And in there you can just say you want y equals u is the output. So you want to say u y is equal to, no, sorry, y is not equal u, y is equal u of 1, right? To the first element on the second element, right? Power, if you like. And you basically, okay, that. Let me go to here, which one it was. Yeah, and then I can display, I don't know, I have another school. Right. So if you run that, then it should give us hopefully the multiplication of the two, which, okay, just thinking about it. Okay, well, it's multiplying obviously, but because of it's varying, it's going to the V times I. You can see it's where it is 1 or whatever it is. It's multiplied by the yeah. So well, it's the wrong I actually. I'm not wrong. Should have measured V here, in fact, across this point. But it's okay. You see what I mean? Yeah.
Okay, brilliant. Thank you.
Yeah. In here you find a lot of components. I think there are batteries and trying to find electric drives. renewables, okay. Solar, wind, facts, power electronics. Machines, obviously, measurement. Yeah, okay. Datasheet, battery. So you can get these models like that. And, you know, inside you can enter the open circuit voltage and so on. And there are many other. So this is powertrain block sets, but there are many other, you'd find them in many other block sets. Network battery, this one. Where is this one? Yeah, so this is a lithium ion battery. And you can put parameters in and so on, time constants, several models. Where is this? I can't remember which block set it is in. Yeah, but you can develop your own function, whatever, to do whatever you like, really.